Now let's look at some op-amp circuits and see how we would analyze those using phasors. So first question is what is going to change with an op-amp? Well, let's consider the simplified model of an op-amp we've looked at before. As we've talked about before, at its simplest, an op-amp is really nothing more than a dependent voltage source. Where we have an output voltage V out and open loop gain times Vp minus Vn, and we have our two input voltages, Vp, Vn, and Ip and In. So we've already looked at this model before in the time domain, where we're just going and showing that the output voltage is simply a function of this open loop gain, which we let go to infinity for the ideal case. And of course, you can always include the output current that's flowing out of the op-amp if we choose to write a KCL equation at the output. So we've already worked problems using this idea. What changes in the frequency domain? As we can see, really nothing. All we're doing is we're changing the labels and turning these into phasor voltages and currents. But that dependent source behaves exactly the same way. And we still have that open loop gain function. So in this case, that means that the three rules still hold. So just as we saw before, first of all, In is equal to Ip is equal to 0 for the ideal op-amp. Rule number 2, given negative feedback, Vp must be equal to Vn. And rule number 3, you don't need to write a KCL equation at the output of the op-amp because it basically is behaving like a defined node unless you need to calculate or determine what I out is. So we're following the same three rules we did before for the time domain. We're just now applying them to phasors. So given these three rules and given this simplified model, let's once again do some ideal op-amp analysis. And let's see what kind of insight we can now get, assuming we're operating with phasors. Let's start with a configuration you're very familiar with. We've seen this before. So once again, we're assuming some source here is generating that Vn voltage. And what I've got here is nothing more than an inverting amplifier configuration, except now I don't have resistors here. Now I've got Z1 and Z2, two generalized impedances, which could be resistance, inductance, capacitance, or some mixture of the three. So in this case, I can now go through and apply the three rules. 0 amps flowing in. I've got 0 volts in the non-inverting input, so I've got a virtual ground. And now I can write my KCL equation. And what I get is that Vn minus 0 over Z2 is equal to 0 minus Vout over Z1. And from here we can easily prove to ourselves that Vout is just equal to minus Z1 over Z2 times Vn. So fundamentally this is no different than the inverting amplifier we saw using resistors as feedback elements, but now we're just basically doing this with phasors and generalized impedance values. All right, so let's take this and let's plug different things into Z1 and Z2. For example, let's assume we let Z2 be a resistor. And let's assume we let Z1 be a capacitor. And so in this case, this will be equal to 1 over j omega c, the impedance of the capacitor. I've got my Vout, my Vn. And I can write the KCL equation for the inverting node, the inverting input node, or I can just go ahead and just plug this directly into here. And what I'm going to get plugging into that equation is that Vout will be equal to minus 1 over j omega c divided by r times Vn, which will be equal to minus 1 over rc times 1 over j omega times Vn. So here's a relationship between Vout and Vn. But you know, that circuit should look familiar to you. We saw this circuit before. We analyzed this in the time domain. This is an inverting integrator. So what we saw before is that V out of t is equal to minus 1 over rc times the integral from t naught to t of Vn tau d tau plus V out at t naught. So this is the answer we got when we analyzed that circuit in the time domain. So let's look at these two and compare them. We note we've got the same minus 1 over rc multiplier. We have an integral in the time domain. We have 1 over j omega in the frequency domain, which leads to a kind of fundamental insight into what's going on in frequency domain analysis. We notice integration in the time domain is equivalent to dividing by j omega in the frequency domain. So here we see what is so powerful about frequency domain analysis. I'm turning integration into algebra. Now along the same lines, I can draw a different circuit. What if I drew this one? Once again, I could write the KCL equation and apply the three rules, but if I once again just take this and realize that Z1 must be R and Z2 must be 1 over j omega c, I can quickly write the solution for this and see that this is equal to minus r over 1 over j omega c times Vn, which will be equal to minus Rc times j omega times Vn. So here's our relationship between V out and Vn for this circuit. And as we may recall, we've seen this circuit too. This is an inverting differentiator. So what do we see from here? If it's an inverting differentiator, that means that V out of t is equal to minus Rc times dVn t dt. Let's compare these two. I've got the same minus Rc multiplier in both. Here I've got j omega Vn. Here I've got the derivative of Vn. So we see our second bit of insight. Differentiation in the time domain. Is directly equivalent to multiplying times j omega in the frequency domain. So here we really understand why the frequency domain is so important, why we study this, and why if you take more advanced courses in signal processing, you'll learn about Laplace transforms and Fourier transforms, which operate along the same idea. You move into the frequency domain, and calculus turns into algebra. Complex algebra, but much, much simpler to manipulate. And this is why these techniques of phasor analysis, of Laplace and Fourier analysis, why we use them so much and why they're so powerful as tools, because they make a lot of very difficult math much, much easier. And this is just a perfect way of illustrating that. Now, let's also consider a couple of other interesting little insights here. And this is always worth pointing out. Then we think about this. Okay, we know that an inductor acts like j omega L in the AC domain. That's what our impedance is. So for AC, but for DC, what does an inductor act like? Well, an inductor acts like a wire, right? We say in DC it behaves just like a short circuit. Well, what is omega in a DC circuit? Well, omega is equal to 0 radians per second in a DC circuit, right? And therefore, Z sub L is equal to J times 0 times L is equal to 0 ohms. So we begin to see here some other things. Up to this point, I've been telling you guys an inductor acts like a short circuit in a DC circuit. A capacitor acts like an open circuit. Well, here's the actual math that shows it. And along the same lines, if I've got a capacitor with ZC is equal to 1 over j omega c. In this case, if omega is equal to 0, in other words DC, then this is equal to infinity. In other words, in DC, a capacitor acts like an open circuit. So we see the same sort of thing. We begin to see how these time domain and DC and AC type things start to link together. All right? Let's go one step further with our op-amp circuits here. What if we had this circuit? Now, in this case, I've still got the same form as that inverting amplifier configuration we looked at before. Only now the feedback impedance is R1 in parallel with 1 over j omega c. So in this case, V out will be equal to minus R1 in parallel with 1 over j omega c divided by R2 times Vn. And if I go ahead and do some mathematical manipulation and simplification to this, I will get the following. This will be equal to minus R1 over R2 times 1 over 1 plus j omega times C times R1 times Vn. So I just skipped a couple of algebra steps and went through and simplified it and got this. Let's consider how this function behaves. Okay, let's consider for a DC circuit, omega is equal to 0. Okay, so I'm going to sketch V out over Vn as a function of frequency. And I'm going to start right here on the DC side. So as a function of frequency, what we have here is that the magnitude of V out over Vn is just this ratio. So V out over Vn is equal to minus R1 over R2 times 1 over 1 plus j omega times CR1. So looking at this, if omega is equal to 0, that term is equal to 0, so we just get R1 over R2, and that is just equal to 1 divided by 1. So down here at DC, the value is just R1 over R2. Now let's consider that as well. When omega is equal to 0, this capacitor becomes an open circuit. What do we have? R1 over R2, okay? That's the magnitude. It's just an inverting amplifier. And so at DC, the capacitor becomes an open circuit, and we've already seen that circuit before. But now let's start increasing omega. Let's let this term get bigger and bigger and bigger. So as omega gets larger, in this case, this denominator, the magnitude of this denominator gets very, very, very large, which means that the magnitude of this term goes to 0. So what happens is as omega goes to infinity, the magnitude of V out over Vn goes to 0. And so we see behavior like this. And this will get smaller and smaller as frequency increases, and this tends towards 0. What we have here is an interesting circuit. At DC, or at very low frequencies, this circuit acts like a standard inverting amplifier. At very high frequencies, V out goes to 0. It doesn't amplify at all. This circuit is selective in its behavior depending upon the frequency of the signal. We have a name to this. We call this a low-pass filter circuit. And what we mean is it passes low frequency signals. So signals that are low in frequency, near DC, they get amplified. They go through the amplifier. At high frequencies, they get rejected. They're attenuated. Well, it turns out this kind of frequency selectivity is extremely useful when we're talking about signal processing. Now, we can do something similar with a circuit like this. What if I've got this circuit? And once again, I can plug this into the same form of that inverting amplifier with generalized impedances. Now I'm going to have that this is equal to 1 over j omega c in series with R2. And so in this case, V out is equal to minus R1 over R2 plus 1 over j omega c times Vn. Or V out divided by Vn is equal to minus j omega times R1 times C divided by 1 plus j omega times R2 times C. So we get this, and we take this equation and do a little bit of algebraic manipulation to it. So let's look at this for a moment. How is this circuit going to behave when I sketch it on a graph like this? All right, let's assume we're at DC. Omega is equal to 0. The numerator is equal to 0. So in this case, I've got 0 divided by 1. That term is equal to 0, but I've got 1. And so V out over Vn is equal to 0. This makes sense. Think about it. At DC, the capacitor is an open circuit. So Vn, no current from this Vn source can make it to this node. All I've got is 0 volts here, 0 volts here, no current flowing through R1, therefore I got 0 volts here. So no surprise there. But now, what happens as omega increases? So as omega goes to infinity, let's think about this. As omega goes to infinity, the impedance of this capacitor gets smaller and smaller and smaller. And so what's going to happen is omega gets very, very large. This term becomes much, much greater than 1. And so what we get is this. So as omega goes to infinity, then V out over Vn goes to minus j omega R1c divided by j omega times R2c. And what do you know? The j omega term cancels and the c cancels, and we get minus R1 over R2. So think about this. As omega goes to infinity, the impedance of this capacitor goes to 0. So Z sub c goes to 0. As omega goes to infinity, it becomes like a short circuit at a sufficiently high frequency, and then this acts just like a wire. And so then what do we have? R1 over R2. Once again, it's an inverting amplifier. So we see this kind of behavior, the opposite of what we saw just a moment ago. As we tend towards omega equal infinity, we converge to a value of the magnitude of V out over Vn of R1 over R2. So we've kind of got the flip side of what we saw a minute ago. Now we are attenuating low frequency and DC signals, but high frequency signals go straight through. We call this a high pass filter because it passes high frequency signals but rejects the low frequency signals. Now we can extend this idea. What if we were to do something like this? What if we had a circuit like this? Here's an input, and I'm going to split it into 3 different types of filters. One is a low-pass filter, LPF. One is a high-pass filter, HPF. And one is a bandpass filter. And a bandpass filter behaves like this. It rejects both low and high frequencies, but lets in a range of frequencies that are kind of in the middle. And so in this case, I have the output of each of these filters. I'm going to give these names, familiar names. I'm going to call this bass. I'm going to call this treble. And I'm going to call this mid-range. In other words, a stereo equalizer. Now I'm going to run these into 3 resistors. And I'm going to draw arrows through these to indicate these are variable resistors. I can adjust them, and then I combine them together. And add another adjustable resistor. So now I've got an inverting summing amplifier. Here's my input, here's my output. This is my 3 controls that adjust the amount of bass, mid-range, and treble for my music that's coming through. And then I have an amplifier with a volume control. And then I feed that output into my speaker system. So what do I have here? I have a stereo amplifier with an equalizer. So here we see a practical application of this idea of filtering, of low pass, band pass, and high pass filtering. Adjusting music so that we accentuate the low frequency, the bass, or the high frequency, the treble. And you will see these kinds of equipment or this kind of concept, for example, used in all music studios when we're adjusting tracks and you're basically adjusting the frequency response of the different tracks in order to mix them together to sound the best. So here's a very practical application of some of these ideas. And of course there are many others. The whole idea behind low pass, band pass, high pass is all the subject of circuits too. And if you take that class, you will learn a great deal more about how these types of filter circuits work. We're not going to really spend any more time on it in this particular class, but once again, it's nice to touch upon some of these concepts so that when you hear them, you will know what people are talking about, even if you don't take any more advanced courses in this particular area. Okay? So that closes things down for our phasor response, our phasor analysis. So you've basically seen all the basics. You've seen that, in effect, most of the same rules apply that we saw with time domain circuits. So next time we'll move into the final portion of this class, and that is the discussion of AC power, what it is and how we calculate it. We'll do that next time.